Hello ladies and gentlemen, this is Dean from Pi, and this is linear algebra. Say you want to translate one set of information to another and create a system that changes any set of that information of the same type. In linear algebra, we call this a transformation, and we denote this at t from v to w. These v and w have to be vector spaces, be them regular like R2 and R3, or abstract like the polynomial space and matrix space. If v and w are the same space, the transformation is called an endomorph or an endomorphism, and these have some special shortcuts that we can look at later. The transformation is then defined by how the information is translated. For example, t from R3 to R2, such that t of x, y, z is equal to x plus y, y plus z, is one way of translating R3 to R2. And t from 2 by 2r to r4, such that t of the matrix ABCD is equal to the vector ABCD, is one way of translating m2 by 2r to r4. Now, as we saw in the last video, when we multiplied a 3 by 2 matrix by a 2 by 1 vector, we got a 3 by 1 vector. And so, from that, you might conclude that the transformation is a type of matrix multiplication, but in fact it's actually the reverse. Matrix multiplication is actually a form of transformation, and all transformations have an associated matrix that fits to multiplication with an element of the domain. And we'll talk about that a bit more in the next video. Now, what if you have two transformations, say T1 from R2 to R3 and T2 from R3 to R4? You want to translate a vector in R2 to R4. Transformations can be composed to let you do this, and this is denoted by a hollow circle. If you have a vector in R2, T1 composed T2 can be described as T2 of T1 of V. So the order of writing the representations is reversed in this description. But T2 is from R3 to R4 and cannot be applied to V. So that does not exist. Compositions are the same as multiplying the associated matrices of each transformation. One neat feature of compositions is that if they are recursive, i.e. T1 is from R2 to R3 and T2 is from R3 to R2, if W is an element of R3, you can infinitely compose these so that T2 composed T1 composed T2 composed T1 and so on is valid, because having an infinite number of transformations before, up to T2 of T1 of T2 of W, it can be found so long as we have T2 here at the beginning instead of T1. Transformations can be described as linear, just like vector spaces. And we prove this slightly differently, though. We want to show that if T is from V to W, and U and V are general elements of V, then T of U plus CV is equal to TU plus C T of V. And also T of 0 has to be 0 always. My professor would get a bit angry because people tended to prove their own statements rather than the linearity. And they just give terrible proofs. First, you want to remember that U plus CV is transformed as a single term. And this will give you something in W which you then need to separate out and factor into T of U plus C T of V. An example would be T from M2 by 2R to M2 by 2R, an endomorphism, such that T of A is equal to A plus 2A transpose. We want to show that this is linear using this same method. So T of A plus CB then is equal to A plus CB plus 2 times A plus CB transpose. Transpositions distribute, which I should have said in the operations video, but it didn't really have an application until now. So then this is then equal to A plus CB plus 2A transpose plus 2CB transpose. This then rearranges to A plus 2A transpose plus CB plus 2CB transpose. And then you factor out the C, and this gives you A plus 2A transpose plus C times B plus 2B transpose. And this is just T of A plus CT of B. So this is linear. Again, like vector spaces, look out for addition of scalars to inspect nonlinear transformations. Since transformations can show linearity, it's not too far of a jump to create a vector space of transformations. These are very large and do not have a very specific formula, so they are denoted L of VW, where L is the space of all transformations between V to W. These are subspaces of M by N R because of the association of matrices, and the dimension of them is given by the product of the dimensions being translated. So the dimension of L R2 to R3 is 6, and the dimension of L from P4 to M3 by 8 is 5 times 24, which is equal to 120, and so on. Compositions can be represented in these spaces too, and the dimension is the same, but you have the added space in there as well, but it's all still multiplication, so the dimension from L of one transformation being between R3 to R4, composed with another being from R4 to R5, so you have to kind of do this grouping, is just going to be 3 times 4 times 5, which is 60. So these two, 120 dimensions and 60 dimensions, are pretty big spaces. An element of this space would have 120 components of information, so it's very detailed and very compact.